The atomic mass for an atom is found on the bottom of the box that the atom is located in. Our atomic mass comes from the fact that not all of the atoms of the element have the same mass. We have different isotopes. And this is why it's not a whole number. We use the average mass of all of the isotopes in order to do our calculation. So this does become a weighted average though, because the abundances are not the same for all the elements. We call that average mass the atomic mass. We have a formula that we use in order to calculate it. And this looks like a complicated formula, but really what we're doing is we're changing that percent abundance into a fractional abundance. So we're moving the decimal place 2 places to the left, just the decimal equivalent to the percentage, times the mass of the isotope. And then we are adding all of those together. The way that we find our atomic mass is we do mass spectrometry. So this allows us to find both the abundance and the mass using this instrument. Now, I'm a little partial to mass spectrometry because this is what I spent all of the years in grad school doing, was mass spectrometry. What we do is we ionize the sample, so we give a charge to it so that we can control it with electrical and magnetic fields. We accelerate it down a tube. Sometimes those molecules are broken into fragments, which allows us to help figure out what the structure of the molecules are. And we accelerate it down the tube. As it moves down the tube, it can be affected by another magnetic field, which spreads the different molecules out depending on their mass. There's several types of mass spectrometers, and they work in slightly different ways. So we bend them to separate them by mass. In our mass spectrum, the information that we get is as a graph. The height of our peak depends on how abundant that species is. So for chlorine 35, it is the more abundant isotope, so it has a taller peak. Chlorine 37 is less abundant, so it has a shorter peak. On the x-axis, that is where we find the relative mass. We're going to find the atomic mass of copper. It has 2 isotopes, so we have copper 63, which has a mass of 62.9396 atomic mass units, and we're told that its abundance 69.17%. And again, this information comes from our mass spectrometer. We also are given that we have an isotope of copper 65, a mass of 64.9278 atomic mass units. Now we're not given its abundance, but because there's only 2 isotopes, we can take 100% minus the other isotope's abundance. And we end up with 30.83%. Now we're trying to find the atomic mass. And in order to do that, we're going to use that equation. Our atomic mass is equal to the sum of of the fractional abundances times the mass of the isotope. And we're going to add those together. So in order to find our atomic mass, we're going to plug in our numbers. Now, fractional abundance, we're just moving the decimal place. So we're basically dividing by 100. And so for our copper 63, our fractional abundance is 0.6917 times its mass. And then we're going to add to that the fractional abundance of copper 65, which again we're dividing by 100, so it becomes 0.3083 times the mass of copper 65. So we do our multiplication and then we add them together. Now notice when it comes to significant figures, we have 6 in each mass, but we only have 4 in our abundance. And so we're going to be limited through this multiplication to 4 significant figures. We're limited to 4 significant figures because of our abundances. So that's 63.55 atomic mass units. Now, to check that we've done our math properly, that final answer that we get, because it's a weighted average, it should fall closer to the more abundant isotope, and it should fall between our lightest and heaviest isotopes. So if we look, we are closer to copper 63's mass, and we are between copper 63 and copper 65. Here is one for you to try. Pause the video and calculate the mass of gallium. Well, we're given gallium 69 with its mass and its abundance. We are also given gallium 71 with its mass and abundance. We can use our equation to find the atomic mass. And we can plug those values in. So remember, fractional abundance is basically dividing our abundances by 100 to get the decimal equivalent times the mass of that isotope plus the fractional abundance, again moving the decimal place, times the mass of the next isotope. And when we do that, 69.72. Again, we're limited to 4 significant figures, so we would report this 69.72 atomic mass units. And again, our average is closer to the more abundant isotope. And it falls between the two. If you look on the periodic table, you will see that this is the atomic mass of gallium.